All right, this is kind of an optional video, just a kind of a companion to the page of notes I gave you. There's a reference page about just parent functions and their relative power. Um, this is something that as we were going through Unit 1, we started kind of making a little bit of a chart on who was more powerful than who, right? And so this symbol that we have in here looks like a less than sign, but it's doubled. And so what that technically means is significantly um, less than. Um, it's not meant to compare just like specific values. Like obviously we could say that 2 is significantly less than 15 billion. But this is really more of a symbol meant to compare functions as they move on and on, primarily towards end behavior is kind of what we're getting at. Most of your parent functions are contained within this chart. We started off with just linear functions. We then reviewed polynomials. Okay, so x to the n is a power function. That means that you're taking a variable to a power, and we did quadratics, which would be if it was 2, and cubics if it was 3, and then we kind of compared um, end behavior for even degreed functions versus odd degreed functions. But really our first 3 parent functions were either linear or polynomials. Linear functions technically are polynomials, but those are all contained in here. And then after that, I think we jumped to rational functions, and you can see rational functions are included. And then we did root functions, and root functions are certainly in here. And then we did exponential and logarithmic functions. Exponential functions are way up here. Oops, there they are. Exponential functions, and logarithmic functions are way back here. Um, then we did some trig functions. I included one in here. Then we did, I think, absolute value functions, and greatest integer functions. We did the logistic function, which I didn't really include, but it would actually be kind of down here in the same category as the sine function if we did compare the logistic function. So most of them are kind of included in here. Um, what we're going to see when we start looking at the graphs is that the value of x is kind of your just moderate growth, steady growth. It's called the identity function. So however far over you go, that's how far up you go. It's got the steadiest growth. If you look at the graph of the origin y equals x, of course you get just a 45-degree line through quadrant 1, which is not growing faster than half pace, not growing slower than half pace, just a real steady graph. But any linear function is going to have fairly steady growth. In fact, it will have constant, a constant rate of change, and that's why they're linear functions. Um, the reason some of these other guys are included, like a constant function, I think we understand why a constant function hopefully is the weakest of all functions. It's because um, if I graph a you know horizontal line, it's never going to grow one way or the other. It's never going up or never going down. Now, why would these two functions be considered in that same category? Well, sine oscillates back and forth, but based on its amplitude, it's never going to get any higher, right, um, than the top. That's its absolute max. It's never going to get any lower than its absolute min. So it's basically a bounded function. So when we start talking about functions that are diverging towards infinity at different rates, does it really matter whether we're saying, oh, this function is always 1 or 5 or 7? where we say this function, well, it never gets smaller than -2 or bigger than +2. I mean, we're talking about something that really is trapped and isn't going to change very much. So that's why sine is kind of included. It's really because of its bounded nature. It's really no more powerful than a constant function. The the reciprocal function, okay, is kind of in there for a different reason. It, it if we were looking at it as it approached zero, it'd actually be a terribly powerful function because it's going up towards infinity. But as it approaches um, infinity, as x approaches infinity, the fraction values get smaller and smaller, and so it's collapsing towards zero. And so this function is, you know, going to be a tiny, tiny value, just like the other ones are when you start comparing really large functions. Um, why do we have some other functions included with x, the linear function? Well, an absolute value function is just like x, except it's going to bend at some point so that it doesn't generate the negative values. But its growth isn't going to change. It's just going to go in a different direction at that same constant rate of growth. And the greatest integer function is every time there's a new integer, it's going to pop up one. So, between the periods of time when x is growing and the greatest integer function is staying constant. So if we just looked at like one little staircase in here, right? In this time, it's very different, okay? But like if you went out 100, x would have a height of 100, and if you went out 100, the greatest integer function would have a height of 100. So in the long term, their values are growing at about the same rate, even though that in the in between integers, one of them doesn't grow at all, and the other one is kind of moving on. So there's definitely some variations in here. There's a little bit of weird stuff going on here and there, but this just kind of tells you how their powers kind of stack up. Uh, if I was going to really point out some of the more important things, I would say always know that exponential functions are more powerful than polynomials. Sometimes people get confused by that. They see something like x to the fifth and they're like, oh my gosh, that is so powerful because 2 to the x is only 2 and this is a 5. But any kind of an exponential graph is eventually going to be more powerful than the power function, even if the exponent was 50. Eventually the exponential function would catch it and pass it. Um, Likewise, logarithmic functions, we just have to understand being the reciprocals of the most powerful function we study in this class, um, are terribly weak. Terribly weak. They're going to always grow. They continue to grow. They don't. Sometimes they look so weak it looks like they have a horizontal asymptote and they're bounded above, but they do continue to grow. Okay. We will take a look at those pictures in a second. Your root functions, some people think those are even weaker than the logarithmics, but the root functions are not. They're fairly slow growing, but nowhere near as weak as the logarithms. So the first chart that you see has a bunch of selected values. I didn't do every single function that's listed above, but I did a bunch of them. And you can see that steady y equals x right in the dead center, right in the middle, and then everything kind of is relative to that. Here I did a line that had a slope that was less than 1. Here I did a line with a slope that was greater than 1, and you can see how the lines will either grow faster or smaller. But then when I start comparing them to either power functions, so I did x squared, and that's going to be much faster growing than y equals 2x, versus root functions, which are weaker. So you can see the root function down here is below 1/2 x. The strength, the relative strength or weakness of these functions becomes apparent as you start looking further out to see what they are doing, how they are bending. The functions that are in the same color are inverse functions. So 2x and 1/2 x are inverses of each other, x squared and root x are inverses, and so they have the inverse growth. One may be really strong, the other one may be really weak. Also, if you remember, inverse functions have a very special property. They are symmetric, okay, reflectively symmetric through the origin, y equals x. And since we have y equals x graphed already anyway, it's kind of nice to see that reflexive property happening, okay? Um, down on the weak end, we've got our constant function down here that's just y equals 1. Pretty darn weak, isn't it? And we have the sine function kind of going back and forth between -2 and 2. But once we blow out, those almost turn into things you can't see anymore. They're so weak. Right now I'm only going up to 30. But if I go up a little bit higher, those just kind of start to disappear into the x-axis because they're so weak. Um, for a while, it almost looks like x squared may be more powerful than 2 to the x, but we can see up here that if we're patient, the pink graph, the 2 to the x, the exponential graph, has already passed x squared by the time we get to about, I don't know, 2 maybe or 3 in here. And you're going to see how much more powerful it is as we continue to follow it up. One thing I probably should have done is included a third graph if I could have found the room, because the inverse functions have the same kind of thing going on. It looks like for a while possibly that log base 2 of x is actually more powerful than x squared, and it is above the, if you go back a little further, it is actually above the root x graph. The pink graph is above the blue graph, but as we get out toward the end, you can see it has inched above it. And what we're going to see on this graph is just how much that exponential graph just blows away the power of the power function x squared. 2 to the x is so significantly more powerful than x squared. That's why when we talk about things that grow super rapidly, we always refer to exponential growth. Now you can see how weak most of these other functions are compared to those two functions. Everything just starts to bleed into the x-axis very weakly. However, if I would have, I should have zoomed way out on the x-axis but kept it low, because I think it would have been worth seeing just how much more powerful the root x was rather than that log function. Just to give you an indication here of how weak the log function is, I'm going to go ahead and take your log. I think we said we were going to do base 2, right? And let's pick a number like, I don't know, 15,000 million billion. What is the log base 2 of 15 billion? I don't know. How about 33.8? Think about that. 33.8. I've gone out 15 billion units on the x-axis, and I haven't even made it up to 50 yet. Not even close, really. On the other hand, if I take the square root of 15,000 million billion, I get 122,474. Compared to 15 billion, that's not a very big number. It's not even close to a million, is it? But at the other hand, when you compare it to 33.8, it's significantly bigger. Significantly bigger. Kind of like when I put, I don't know, let's do, 8 squared. We know that that's 64. Whereas if I do 2 to the 8th, that's 256. That's 4 times bigger already, and I'm only comparing eighths. It's going to be more substantial the further out on the x-axis I go. So hopefully that helps understand a little bit about the nature of these graphs. If you do understand who's more powerful than who, it makes evaluating things like end behavior so much easier, because I can, let's say the two functions I was comparing were like log of x, which we know is pretty weak, and x, which isn't that special, is it? X seems to be pretty pretty weak graph. Well, now if I was doing a comparison where I was doing x, the limit of x plus log of base n of x, and I wanted to know where that was, what was the end behavior. Well, I know that x is more powerful than log of x in both directions. Actually, log n of x wouldn't even be defined to the left of the x-axis, less than 0. But x is more powerful, so the further out I go, this graph's just going to behave like x. And if I was going to compare that as an end behavior, like this, I could say, oh, the bottom of this fraction is way more powerful as I head to infinity. This thing's going to collapse to 0. Or, hey, look, this time the numerator is more powerful than the denominator. And so as I move towards infinity, these values are going to continue to grow, and it's going to diverge towards infinity. So once you know who's more powerful than who, you have the ability to really make some much higher level comparisons regarding these types of limit problems, discussing end behavior and end behavior models, and just understanding what things are going to look like the further out you go. So hopefully this helped you understand that sheet a little bit more if you were not sure about it, and hopefully the sheet provides a nice reference as you're studying for the limits assessments and even the final exam. Thanks for listening, and see you.